Hello guys, welcome on Tesla Adventures. In this video, we'll discuss the Wien's displacement law. So first of all, we know that each body whose temperature is greater than 0 Kelvin obviously radiates some radiations of almost all possible wavelengths. It is a different matter of concern that each wavelength has some different emissive power, but it radiates almost all possible wavelengths. Okay, so let me explain you this Wien's displacement law with an example. So let us assume that this is a radiating body which is radiating these three wavelengths, which is 10 angstrom, 5 angstrom, and 3 angstroms. And the emissive power of this particular radiation is 2000. The emissive power of this radiation is 4000, and emissive power of this radiation is 6000. Now we can clearly see the maximum wavelength of the radiations emitted is 10 angstrom, but we are concerned with the wavelength which is corresponding to the maximum emissive power. So in this case, the maximum emissive power is this one. This is the maximum emissive power. Okay, so the wavelength which corresponds to the maximum emissive power, in this case it is lambda 3, is called as lambda max. So lambda max is not the maximum wavelength. In fact, lambda max is the wavelength which corresponds to the maximum emissive power. Okay, so it is not necessary that the radiation which has a maximum emissive power has also the maximum wavelength. Okay, so you must clearly know that lambda max is the wavelength associated with the radiation whose emissive power is maximum. So in this case it is this lambda 3. Now, this law states that the maximum wavelength emitted by a body is inversely proportional to the temperature, which means that if temperature of the body will increase, then the maximum wavelength emitted by that body will in fact decrease, and the maximum and the frequency emitted by that body corresponding to the maximum emissive power will increase. I can give you a realistic example of this fact, that when we feel when we see a gas flame, when we see a gas cooking gas, and when we see its flame, in most of the cases the gas flame seems to be blue. So which means that the radiation which that flame is emitting is in the visible region, and it is blue or ultraviolet. Okay, so violet, ultraviolet, blue. So the radiation emitted by that flame is bluish. But as we see that when we spill some amount of water on that burning flame, then suddenly its color changes and it becomes reddish, oranges, yellowish. So you understand that in Vibgyor, the yellow color, orange color and red color frequency is less than the frequency of VIB. So if we spill some water on that gas flame, then due to water its temperature decreases slightly. So due to decrease in that temperature, the maximum wavelength emitted by that gas flame will be now of some higher wavelength, and will be in fact maximum emissive power of that gas flame will be now have some higher wavelength and lower frequency. So that bluish flame will suddenly appear to be reddish, oranges or yellowish. So another example I can give you, that when we feel sickness, when we feel fever, our body temperature rises, and the person which is observing us, or the person which is observing our face, observes that our face or our body becomes reddish. Because this is due to the fact that when our body temperature rises, then the maximum radiation frequency of emitted by our body also rises, and in fact frequency rises and wavelength becomes lesser. So in that case, the radiation emitted by our body is coming in reddish region and infrared and red region. So slightly our face appears to be red, and there are many examples of this theory, Wien's displacement law. I think you must have understood the example of gas flame and the body temperature example. So this is the Wien's displacement law, that when we will increase the absolute temperature of any radiating body, then the wavelength that that body is emitting, which is corresponding to the maximum emissive power, decreases. Okay. Now when this proportionality sign disappears, then a constant comes which is called as Wien's constant, and this Wien's constant has a value of 0.282 centimeter Kelvin. You can see the unit. This is centimeter, this is Kelvin. So this is Wien's displacement, Wien's constant. And if we draw the graph between spectral emissive power and wavelength emitted by radiation. Now what is spectral emissive power? Now you can see that this is the total emissive power of this radiation. So if I divide this emissive power by this wavelength, then it would be the spectral emissive power of this wavelength. So now you can understand that the spectral emissive power is the emissive power of a particular wavelength per unit that wavelength. Okay, so this is spectral emissive power. So if I plot the graph of spectral emissive power with the wavelength of the emitted radiation, then this graph appears to be like this, which means that you can see that this peak represents the maximum spectral emissive power, and the wavelength corresponding to this peak is lambda max. So if we increase the temperature of the body, this graph is at 2000, in fact this is 1000. So if we are increasing the temperature 1000, then 1500, then 2000, then we can see that the lambda maximum is decreasing. Okay, so this is the Wien's displacement law. And obviously if we say that the total emissive power of the body, total emissive power, so in this case the total emissive power would be sum of all these emissive powers. Okay, so we can also write that in this case the total emissive power would be E1 lambda into lambda 1 plus E2 lambda into lambda 2 plus E3 lambda into lambda 3. This is the total emissive power emitted by this body. So if a body is emitting all possible radiations which are having the wavelength in the range of 0 to infinity, then we can also say that the total emissive power would be integration of E lambda d lambda from 0 to infinity. And this total emissive power, you can see that the area of this graph, the area bounded between this graph and wavelength axis is obviously E lambda into lambda. So this area of this graph area of the graph will give us E total emissive power. So and we also know that the total emissive power is directly proportional to the fourth power of the absolute temperature of the body, because we know the formula that E total is equal to sigma E T to the power 4. Okay, so if we are increasing the temperature of this of a body, then the area under this graph will also increase to the fourth power of the temperature. So we can conclude that area of this graph A is proportional to T to the power 4, and the peak wavelength, the wavelength at the peak is inversely proportional to the temperature of this body. Now, what are the conclusions of this graph? The first and the important conclusion is the fact that the area of this graph represents total emissive power, which I have already explained. The second conclusion is the fact that the emissive power of a body is directly proportional to the fourth power of the absolute temperature, which I have already explained, and therefore the area under this graph and wavelength axis is directly proportional to the fourth power of this temperature, absolute temperature. Now, for a given wavelength, for a given temperature, there is a particular wavelength for which the radiation energy is maximum. I have already explained, and we know that if the temperature of the body is doubled, then the wavelength corresponding to the maximum emissive power becomes half, and the area under this graph will become 16 times, because it is dependent on T to the power 4. So this is the Wien's displacement law, and in next video we'll discuss the solar constant, which is a very important factor, and we'll use that in calculation of the sun's temperature. Thank you.